Welcome to the 11th lecture of Analog Integrated Circuits Design. So far we were discussing about common source amplifiers. We looked at the various loads. Uh, if you Yeah, so this is the place where we listed out all the varieties of common source and we have discussed one by one. Now at this point, I hope that you can definitely say the gain expressions for all this. You can talk about the output DC level of all these loads, and also the advantages or the trade-off between some of the parameters. All right. So in today's class, in last class we also saw the analog design octagon, and I have made some comparison with the normal common source amplifier and a degeneration. So in today's class we'll continue our discussion and we'll quickly go through common drain amplifiers and common gate amplifiers so that we can complete all the single stage small signal amplifiers, and then later we will proceed with some other topologies like cascoding technique, folded cascoding technique, and then we do have something called as differential amplifiers to complete this unit 1. So in today's class we'll start with common drain amplifiers. So as the name suggests, when we say common drain amplifiers, the drain terminal will be common in this case. When I say drain terminal is common, the drain terminal will act as a common point between both input and output. So since drain is common, and one more thing, if you remember, we told that when we say common source, in most of the cases, source will be common, or source will be ground, or source will be VDD. That means for small signals, there will be a ground terminal directly connected. The same thing applies even to common drain. So when we say common drain amplifier, it doesn't mean that drain will be connected to ground always, but for small signals, for small signal voltages, yes, a drain will be common, or drain will act as ground. So this is one such case. Drain should be common. So I'm just connecting that directly to VDD, and we know that VDD will act as a zero or a ground for small signals. Input is connected to gate, and output is taken from source. This is V out. All right. So what we need to understand here is we are connecting. Input is at gate, output is sensed at source, and the drain terminal is common. Drain terminal is common for both input as well as output. So to have a complete circuit, so usually as we have started with common source with the resistive load, similarly here I will just add a resistive load here. Since it is connected to the source terminal, we call this resistance as RS, right? So input is given to gate, output is taken from source, drain is common, and this amplifier is a common drain amplifier. Now if you look at this amplifier circuit and say if you are increasing the input voltage, as input voltage increases, you can definitely say that when I say input voltage increases, you are increasing the voltage at gate. So when your gate voltage increases, definitely your drain current will increase, your ID will definitely increase. So for a DC voltage, there will be a DC current here. So if ID is increasing, you can directly see that V out will increase, right? Because V out is taken from the source. Now you can see that I have used two notations here. Here you will see I have just written a small letters V out and V in, just to show that small signal input is applied at gate and small signal output is taken from source. Now if you look at this, I have written normal or capital V in and capital V out. mean to say that for large signal voltages variation, so when you increase your input voltage from a small value to a large value, your drain current will increase, and as a result you can see that your output voltage also will increase, right? So if I'm asking you to write a relationship between input and output voltages, say large signal voltages, what will you write, or how will you write? Are you guys with me? Can I get some response in the chat box? Are you guys with me? Yes. Yeah, voltage gain. I'm asking you the relationship between the voltages. Say, for example, from here to here you have V in, here to here you have another voltage, and from here to here you have V out. If that is the case, how will you write the relationship between V in? So this is basically VGS, right? So V in, VGS, and V out. So I can write KVL. If I apply, I can write that V in from here to here minus VGS minus V out is equal to 0, or I can write V in minus VGS is equal to V out, right? Or to be very precise, yeah, very good, Bhuvan, you have written V in is equal to VGS plus V out. That is true, that is right. So what is observed here is, uh, you can always say that your input voltage and output voltage will have a difference of VGS voltage, right? So that can be considered as a DC voltage difference when I consider V in and V out as large voltages. For this reason, we call this as this amplifier as, or this configuration as level shifters. What is the meaning of level shifter? You are applying some voltage at input, but that voltage with amplification, we'll talk about the amplification factor of this circuit a little later. But if you provide something here, we know that you will get output from here. But if you look at the DC condition of those two signals, say you have input signal here, which is on a particular DC level. I'll write this as some DC level, say DC level 1. Now your output voltage is at another DC level. I'll say DC level 2, and these two DC levels difference will be always VGS. That is what we observed here. For that reason, we will say this circuit or this amplifier circuit act as a level shifter, right? And probably you'll remember that another name for this, we call this as source follower also. We will see the why it is called a source follower. The reason is source terminal is the output terminal. This terminal always follows input. The source terminal always follows input, or we can say that the output voltage is exactly or almost equal to input voltage. So as a source terminal is following the input, source terminal follows input, and for that reason we call this as source follower, right? Now one more thing. So if I look at the variation, say I'm just drawing a time response. Here I'm plotting voltages. What I want to say here is, say if your input voltage is increasing in this pattern, input voltage, when I draw a line like this, what I am conveying is, if you are increasing your input voltage over time, this as from a low value to high value, your output also will increase. Your output also will increase by maintaining a constant voltage difference, or by maintaining a difference between these two as VGS. Right. Again, I'm coming to the point that this can be treated as a level shifter. So there are many cases, say for example, when we connect from one amplifier to another amplifier, and we observe that both amplifiers have, say I need to connect a particular signal from the output of a circuit to another block or another circuit, but both have different DC levels, right? You can look at this. One is operating at this DC level, another is operating another DC level. So if I want to have a signal flow from this point to that point, but with this DC shift, I can definitely plug in a common drain amplifier in between, get this level shift by properly choosing the WL values, and by properly setting the VGS of the transistor, we can easily configure, we can easily cascade from one stage to another stage. Right. This is one of the very common application of common drain. Apart from this, we do have several other applications also. So, is it clear so far what I discussed? Can I get some response here in the chat box? Say yes or no. Is this clear, or do you have some questions? All right. Okay. Now, see, our main interest is to yes, Avinash. Yes, what I was telling is, say you have two different. You have a particular block available here. You have some. You are getting some signal. This signal is a signal at the output of this block. Now, for your application, you want to connect or you want to give the signal to another block, and this is another block sitting, and the input of this block is having this particular DC, say DC2. Now, how will you connect this to this, because both are at two different DC levels? Now, when you want to connect between those two different DC levels, the easiest way is to have a level shifter in between. The level shifter is this common drain amplifier, because uh, if you see, you know what is this DC level, you know what is this DC level, and you also know what should be the difference between those two DC levels. In that case, you can definitely configure a common drain amplifier and plug that in between, so that you can avail or you can get the suitable DC shift and thereby connect this block to this block by keeping a common drain amplifier in between. Okay, another question is, can you explain a source follower? Yes, it is called a source follower because the source terminal will always follow the input. Yeah, for another see, while explaining this, I should also say that when you keep common drain in between, you are getting the suitable DC level, but this common drain should not affect the signals, right? The signal strength. If I am getting this level here, I should get the same thing here. That means common drain should not amplify the signal. That is another reason we common drain amplifier have an for a it is having a gain of 1, and that is the reason why we call this as source follower. The source follow input, the meaning is the source voltage or the source the signal available at source is same as the signal available at the gate. Source terminal will follow input. That is why we call it a source follower. Okay, so let us quickly see the small signal analysis of this common drain amplifier. Small signal analysis. So anyway, you are familiar with this, but we'll start by just writing with by considering both lambda and gamma equal to 0, which is very familiar for you. Yes, Anushka, your question is DC level of the amplifier stage is determined by VGS. So I didn't understand in which context you are asking. Um, Which amplifier stage? So I was talking about there is one something here, there is something here. Now in between you can actually keep the CD amplifier, and the CD amplifier will definitely the value what I can say is the W by L value or the drain current of this common drain amplifier will definitely set this VGS.
So, as in, like the DC values are different of like the first stage and the second stage because of different VGS, right?
No, not because of different VGS. I was talking. See, when you say VGS, if you're referring to the DC voltage, yes, it is dependent on the DC voltage. That is true. Yes, that is true, Anushka. Yes. All right. So let me quickly go to the small signal analysis. So I'll be. If you have doubt in this, please pause me in between, because I'm just assuming that you know this, even though I'm yeah, this is VGS and this is GM-VGS, which is the transistor small signal equivalent. Now look at the circuit. We are providing gate input at gate, so I can directly mark this as V in. This is V in. What about drain? Drain is VDD, but that should be acting as common point for the AC signals. So that is grounded. Now the other side, let me just use a different color just to say that whatever is in blue is the equivalent of transistor, and rest the modifications what I'm doing is for the circuit. Okay, so this is RS and this is the output point V out, where this is V in, right? Now, if you remember, we can write the output voltage V out as the current flowing through RS is nothing but GM VGS, which is a signal current, into RS. Now, what is VGS? VGS is V in minus V out itself, right? So by substituting this here, I can write V out as equal to, V out can be written as GM into V in minus V out into RS, right? Or we can write V out by V in as GM RS by 1 plus GM RS. GMRS by 1 plus GMRS. From the equation itself, you can say that your voltage gain is definitely less than 1, or with an approximation, I can say this is approximately equal to 1. What is approximation? If your GMRS is larger than 1, say your GMRS is having a value of 10, in that case, if you can easily neglect 1 and write it as 1. Your voltage gain is equal to 1. What is the meaning? V out is approximately equal to V in. Where is V out? V out is appearing at the source terminal. So what is source doing? Source is simply following the gate terminal. That is why we call this as source follower. All right. Now, just elaborating on this, we know that AV is GMRS by 1 plus GMRS. This can be further written as, by taking GM common, I can write this as RS divided by 1 by GM plus RS. Now, what I'm trying to do here is, for every amplifier, for whether it is common drain or common source or common gate, all the amplifiers, the gain without lambda and gamma, or the ideal, just with the ideal MOSFET, you have straightforward ways to write the gain. In the case of common source, you know that the resistance available at the drain divided by resistance looking into source, RD by 1 by GM was written as GMRD, that is a gain of CS amplifier. Similarly, here also, by looking at this expression RS by 1 by GM plus RS, you can have a formula here to write the gain of a common drain when there is lambda and gamma equal to 0. You can think of gain as total resistance at the source terminal divided by resistance at source terminal, again that is RS in this case, plus resistance looking into source, terminal, that is 1 by GM in this case, right? So if you look at this, okay, let me redraw that here. If this is the case, this is V out, this is V in. So as per this observation, the total resistance is RS. Now again, in the denominator, you have to put the same RS plus the resistance looking into source, which is equal to 1 by GM, right? Now this is a shortcut way to write the gain expression for a CD amplifier, right? So, but this is familiar for you. I am just considering now. The next step is to consider both lambda and gamma, because that is the what we are doing in this particular course. We are looking at the effect of body also here. So let me write this as small signal analysis. So if you have questions, please put in the chat box. I can reply to those questions. Now I'm doing small signal analysis by considering both lambda and gamma not equal to 0. The first case was I just ignored or neglected both lambda and gamma, right? So that means now I have to take the equivalent circuit of MOSFET, including gamma and lambda. So GM VGS. This is VGS. Since lambda is included, I have to include this R naught. Since gamma is included, I have to include this GMB VBS. This is the equivalent of MOSFET. Right. As I mentioned, for to understand that, uh, yes, Sriharsha, your question. You were asking for the previous circuit. Oh, all right, yeah. So the previous circuit, the resistance looking at the output, yes, the output resistance can be observed as 1 by gm parallel to rs, or you can directly say that your output resistance is very low. Yes, yeah, sorry, I didn't mention the output resistance. That is right, Sriharsha, it is 1 by gm parallel to rs. All right. So now what I have to do is I have just placed the small signal equivalent circuit of MOSFET. Now I need to add the additional things here. So on this side I have to add V in. On that side drain should be connected to ground, and here I have to connect RS. And this is V out. Right. Now, so in several ways you can write this, or progressively you can write first for lambda and then for gamma, but I have taken it together because I hope that you guys can definitely understand if I write this together. So one thing, you have to make some observations here. One is, this is drain side and drain side is grounded. Similarly, from source side through a resistance it is grounded. Now you can see that this is the common point where RS is connected to ground and R naught is also connected to ground, right? So in fact, in the circuit, RS and R naught are in parallel. Since they are in parallel, I am just marking both parallel combination as RS dash just for simplicity, because we have two resistors, those are in parallel. So I just wrote the parallel combination and I marked it as RS dash. Now, how will I write the expression for V out now? What is V out? So V out can be written as the total current flowing through RS parallel to R naught into that resistance, right? So what is the current flowing here? It is equal to GMVGS plus GMBVBS, that is the total current. That should be multiplied by this RS dash, which is R naught parallel to RS. I hope this is clear. Now I will just write what is VGS and what is VBS from the same equivalent circuit. What is VGS? VGS is this node voltage minus this node voltage. What is VGS? It is simple. It is V in minus V out. What is VBS? Body is connected to ground, so it is 0 minus V out is, sorry, VS is V out. So what is the meaning of minus VS? Similarly, it is VB minus VS. That I substitute and I got those results. Now what we'll do, we'll keep these two and substitute here, so that we can write the expression for V out as GM V in minus GM V out minus GMB V out, the whole thing multiplied by RS dash. Or if you rearrange this, you will get it as V out by V in as GM into RS dash divided by 1 plus GM plus GMB into RS dash, right? So this is as same as the previous expression. In place of, so you have, okay, I'll tell you the differences. This can be further written as, if you take 1 by GM RS dash, sorry, if I take GM RS dash common and if I'm cancelling it, I can write this as 1 by GM RS dash plus, here I'll get it as 1 plus eta, because previously you would have noted eta is a factor of GMB by GM. This can be further written as or this can be approximately, we can, if I'm ignoring or neglecting 1 by gm rs dash, I can write this as equal to 1 by 1 plus eta. So these equations I have just written for the sake of writing. So if I look at these expressions, the gain, the initial gain what I wrote is gm rs by 1 plus gm rs, and now gain with the lambda and gamma I have written as gm rs dash divided by 1 plus gm plus gmb into rs dash. So you can definitely note the difference. In rs dash I have included r naught, and body effect should be added along with the gm in the denominator. That is how you should compare and see how uh, this channeling modulation and gamma has affected the voltage gain. Right. I hope this is clear. If you have questions, you can ask now, or you can think over this. Meanwhile, I'll give another question for you to work out. So what you can do is, we have started with a simple NMOS common drain amplifier with a resistive load. Now in place of that, we have a transistor which is suitably biased in saturation, VB, which is M2. This is V in and this is V out. So this is VDD, this is M1. Now also assume that both bodies are connected to ground. Yes, since it is NMOS, it is connected to ground. The question is, find the voltage gain of this circuit. You can do in either way. One, you can either you can go with the small signal equivalent circuit and derive an expression, or use the existing expression, because we already derived the expression, and you can substitute in that expression and get the final value. So I am expecting answers from your side. Found the GM in the numerator changes GM plus GMB. So Akash, it is not. Yeah. So I wanted to tell that the idea of adding this GMB is not like wherever GM is there you have to add GMB. We have properly derived it. You can see here we have derived it, and in that derivation we got only GMB in the denominator. Why? Because the relation between the input and output is in that way, right? So since I have just made a comparison here, and it is not that you are in your expression you have directly add GMB to all the GMs, especially from CD amplifiers onwards, right? uh, I hope that is clear. So one more thing, one more thing what I was telling is, if you have a transistor, input transistor, where your source is grounded, and if at all if it is having a body effect, that means if a VSB exists, in that case you can directly add GMB, right? But now you can see that at the source channel you have a load connected, right? So in such cases you cannot add GMB directly. That is why I have derived the expression first and then later made a comparison. Yeah, thank you Akash for asking that. Now the question you can see on the screen now. I expect all of you to work out this, and I can check with some of you guys. Alan, Aji, are you there?
Yes, sir.
Yeah, Alan, can you tell me how will you write the voltage gain expression for this? I'm not asking the final expression, but you can see the expression already on the screen. So looking at that, can you tell me what all changes I should make?
So probably the RS, because we look at the top and towards the bottom, sir.
Okay, so what I should do?
There would be an there would be extra resistance, sir. R naught.
What is that? What is that extra resistance?
R naught, sir.
R naught.
And from
okay.
the from GM into GP, R naught, sir.
Okay. Any other answers? Okay, thank you, Alan.
Yeah, I can tell a final expression. It's
Oh.
1 by GMB parallel RO2 parallel RO1 by 1 by GM1 plus 1 by GMB1 parallel RO2 parallel RO1.
Okay, so from where do you get this 1 by GMB term? Amog, can you?
Body,
Sir,
it's a body effect.
yeah, I know that is body effect, but my question is, how did you get that value in parallel to the resistance?
Because if you do GM plus GMB and if you further simplify it, you'll get that. It'll be
Oh, is
GM
it?
plus GMB, no? So it'll further simplify.
Yeah, but GM plus GMB, if you further simplify, how will you get a 1 by GMB term? I'm not sure about
Because
that.
because you'll get
Yeah.
if you like further.
Okay, okay, Amog. Yeah, I'll try to explain that. Any other answers? Anyone else got any other answers? Okay. So what we do here is we'll proceed with the same equivalent circuit, and let's see how we can write it. Okay. So the top M1 is our input transistor. So I'm just replacing input transistor with its equivalent, which is GM VGS. When you have a VGS voltage plus minus here, and that should be continued by the R naught value of that, R naught 1. And one more thing is the GMB VBS of that. This is for the input device, and this point is grounded. Now here M2 device, you can clearly see M2. I'm interested to find the resistance here. Gate is connected to VB, but for small signal gate will be ground. Looking at drain, this resistance, by considering channeling the modulation, I can directly say that this is equal to R naught. Since it is M2, I will write this as R naught 2, and this is the output node V out. I hope this is clear what I have drawn now. Now I will do small changes here. As discussed before, this R naught 1 and R naught 2 both are in parallel, right? So by drawing R naught from this point to ground is as same as drawing this R naught 1 from sorry from here to ground. Both are same. This is R naught 1. All right. Now, now you can see there is a current source here, which is connected between this point is drain and this point is source. Yeah, sorry. So now we can see that this point is uh, source and this is drain, and you have a current source connected across that, which is GMB into VBS. Now, what is VBS? VBS is VB minus VS, which is equal to 0 minus VS, because body is grounded in this case. So VBS is as same as VS voltage. Now, looking at the current source, you see drain is connected to ground and the other end is connected to uh, source, right? Now, what you have here is a current source whose value is GMB VBS. What is the voltage across the current source? This end you have ground, which is same as body voltage. This end you have source, which is VBS voltage, right? So if you remember in the initial discussion, so whenever you have a current source and the controlling voltage is VBS, right? Now the voltage across the current source is also same as VBS. In such a case, you can represent this current source as a resistance. We have discussed the same thing. The by same method only we represented R naught from G naught VDS. I hope you remember that. In that case, what is the value of this resistance? This resistance can be marked as 1 by GMB. This is a simple thing what you need to understand. So what I have done here is I have a current source whose value is GMB VBS. When I looked at the voltage across the current source, that is same as VBS, because one end is grounded as body, other end is connected to source. So if there is a current source whose terminal voltages are same as the controlling voltage is same as the terminal voltage. The variation, if there is a VBS change, your GM VBS, your current will vary in proportion, so that can be represented as a resistance, right? So I hope that is clear for at least for few people. If you have question, you can ask. Meanwhile, I'll just complete this. So what I will do now is, this is the circuit, right? Now I understood that GMB VBS can also be represented as a resistance. If that is the case, I will add that resistance here. This is 1 by GMB. And this is same as common. Now, if I want to write V out by V in, can you just look at the previous observation what we made, or can you look at this circuit diagram? The circuit diagram is same as before, right? In place of RS, now you have three resistors in parallel. One is R01, another one is R02, another one is 1 by GMB. So you can use the same formula, which is RS divided by 1 by GM plus RS. So in place of RS, you have R01 parallel R02 parallel 1 by GMB. I'll mark it as 1 because it is a first transistor, divided by 1 by GM1 plus the same resistance R01 parallel to R02 parallel to 1 by GMB1. So for how many? Yes, yeah, that is why Amitesh. Yeah, I just wrote it as GMB1. For the second transistor, there is no body effect because source is connected to ground, body is also connected to ground. Is this clear? So how many of you understood this the way I have written? The same, I have drawn the equivalent circuit and then I have just modified, rearranged the equivalent circuit. That's it. Can I get some response by the final equation? Can you please explain? Yes, Amitesh. So this expression is same as the expression what I have written first. 1 by GM plus RS. This is what I have written for the basic amplifier. Look at this. Look at the equivalent circuit. This is the equivalent circuit, right? If you look at this equivalent circuit and the circuit what I have drawn here, the only difference is in the previous equivalent circuit at the source you have one resistance RS, but now you have three resistors in parallel. So in the same expression, in place of RS, I put all the three resistors in parallel and I got this expression. Is this clear? Okay, so the thing to understand, or the only thing what you need to take care here is this. Whenever you have a current source, whenever you have the controlling voltage and the voltage across the current source same, that can be represented using a resistance. The same thing we have taken even for the channeling modulation when we develop the small signal model. Yeah, now if this is clear, let me give you one question. This one. Usually we start with idle current source, but now I'm just giving this as the last one. Being this is VDD. Yeah, the question is, what is the output resistance of this and voltage gain? So what will be voltage gain?
Sir, here it will just be R naught, no output resistance.
Output resistance will be
R naught, because the thing is, current sources have to be shorted in small signal and zero.
no current
Yeah.
current sources should be made open. in the small signal equivalent circuit, not
I'm
short.
no open. That's what. So this will be like the RS will be zero, right?
No, RS should be infinity in that case. Because for
Okay,
an
thank
ideal
you.
current
Yeah.
source, for an ideal current source, the voltage across should be infinity. So infinity in parallel to the resistance seen up. So say I just put lambda equal to 0. Why I put lambda equal to 0 is to for you guys to write the other resistance. If your lambda is there, there is R naught parallel to some value. What is a resistance seen up? Resistance seen up should be 1 by Gm since it is source. Now body is also there. I can say it is 1 by Gm plus GMB. That is output resistance. Now R naught is there, that will be in parallel to infinity, because that is the resistance across the current source. So if those things are not there, I can write it as 1 by Gm plus GMB alone. The input resistance is infinity because still input is available at the gate. And what about voltage gain? Ideally, I can say voltage gain is very closely equal to 1. Right. In this case, I can say that because I know that is GMRS by 1 plus GMRS, or I will say it is 1 by GMRS plus 1. Right. So what you have in terms of RS is infinity. So your voltage gain is very closely equal to 1. Now, if I look at these features, so R out you can see it is 1 by Gm plus GMB, which is actually a very small value. So your voltage gain is equal to 1, R in is equal to infinity, and R out is say low value, very low value. Now, if I look at these features, if I closely look at these features, these are the features of a voltage buffer. What do you mean by voltage buffer? Voltage buffer are units which are introduced between two blocks in order to get the same voltage here. Voltage will be buffered. Voltage will be whatever voltage is available here, the same voltage will be buffered and will be available here. Now, why we use voltage buffer is because of this. Since it is having infinite resistance, input resistance and very low output resistance, whenever you need to connect between 2 points, where one point is having, or whenever you want to connect between 2 points which is having unequal impedances, say this is at impedance 1 and if this is at impedance level 2, and particularly if this is a high impedance and if this is a low impedance, in such cases we use this buffers in between. This is basically used for impedance matching. You'll see this in little more detail. Impedance matching, right? So this is another use of voltage common drain amplifier. We use this as for impedance matching. All right. uh, then for every case of CD configuration, we can directly write AV equal to 1. Yes, see, AV, the maximum gain is 1. And that is, I can say that is an ideal case. So your gain will be always less than 1. It will be 0.99 and 0.998 in that range, right? So how ideally we can design CD amplifier is what we need to take care when we do design. But as having said that, if you are asked to write the voltage gain expression for a question as something what you can see on the screen now, if you directly write 1, yes, I'll appreciate that because you identified that is a common drain amplifier. But you may not get marks because what we are expecting by giving the circuit diagram is to arrive at this kind of expression. So after writing all this, if you're equating it to 1, that is perfectly fine. Is it clear, Sri Harsha? Yes. Okay. Moving on, I'm just quickly, I'll also talk about some of the limitations of this CD amplifier. So one limitation of CD amplifier is with respect to the non-linearity. So you will be wondering, what is this non-linearity? Let me explain that with the help of a small equivalent circuit, small circuit diagram. This is VDD, this is V out, this is V in, and this is RS. Right. Now, when we explain this, we did not consider the body effect, but we know that for this, body effect will be definitely there. Right. So from the previous discussion, I wrote V in minus VGS is equal to V out. So whenever V in and V out are related, and always the difference will be VGS is what we mentioned, right? And if you remember, I have also drawn a diagram something like this, where you have V in of this variation and your V out is varying like this with a constant VGS difference here, right? Now, if you closely observe, as you increase your V in, what happens? Definitely your ID will increase. Now, as your ID increases, your V out will also naturally increase, because you are lifting this voltage, that is increasing your ID, that is thereby you are lifting this voltage V out. But now one thing you need to observe here is, as your V out is increasing, the source terminal is also increasing, right? Vs voltage is also increasing. Now what is happening when we consider body? If source voltage is increasing, your VSB voltage will in turn change, or your VSB voltage will increase. So this is your VSB voltage, sorry. Your VSB voltage will in turn increase. So what happens if your VSB increases? We know that that will lead to a change in threshold voltage, or VT, right? Now if VT is changing, definitely your VGS will change. How? We know that VGS is equal to VT plus under root of 2 ID by mu and C of W by L. Now with all these changes, if VT is varying, if this VT is varying, your VGS will vary. What is the meaning, or what is that for us? If your VGS is changing, what is the meaning? As there is an increase in V in, your V out will increase, and that increase is now not like a linear change, or that is not by keeping a constant value of VGS in between. Rather, as you keep on increasing, your V out will be having a variation something like this, because this difference is going to increase, right? So previously you can see that V in and V out both had a linear relation. What is linear? As V in increases, V out also increases in proportion. But now because of this body effect, your VGS is going to increase, and thereby the difference between V in and V out is not staying constant, but it is actually varying, and this causes some kind of non-linearity. Is that clear? Is it clear? Can I get some response? So V in and V out will not have a constant difference VGS, rather VGS will vary, and that lead to some non-linearity. All right. Similarly, we need then it is not ideal for source shifters. I didn't get that. For level shifters is what you meant.
Yes, sir. Yes, sir. So,
Yeah. So we cannot say it is not ideal. It all depends on what range of input and output voltages you are using, and how much non-linearity is allowed for that particular system, or how much we can tolerate within the system. All right. Yeah. So coming to one more point with respect to the drawback or some limitation, we call this as voltage headroom limitation. Voltage headroom limitation. So for this you need to understand, whenever you have a CS amplifier, what is drawn first here, this is CS amplifier with this as V in and this as V out, and whenever I do cascading of the CS amplifier to this, whenever, so I was telling we will be connecting CD amplifier at the output of some other amplifier. So assume that this is your first amplifier, and let me draw the voltage headroom of this. This maximum is VDD, this minimum is say 0 volt, and this is VDD and this is 0, and you know that this output DC will be at VDD minus IDRD if ID is the current flowing here. So let me mark that value as somewhere here. Use a different color. I think this is green. Yeah. Yeah, they say this is VDD minus IDRD, which is the output DC level of this common drain amplifier. Right. Now I can say that this output, if you have an output voltage to swing at this point, right, the maximum can go up to VDD, but if it goes to VDD, there is no if this point goes to VDD, there is no drop across RD, right? So but the minimum level cannot go to 0 because I need to sustain the saturation condition of the transistor. So I can roughly draw it as something like this, where I need to have some overdrive voltage reserved here to reserved for the output voltage, sorry, the transistor M1, VOV of M1 transistor. Now we know that we will not have what to say, we will always have a symmetrical swing across the DC. That is what we do. So I can draw something like this. So this will be the voltage available at the output. Right. Now listen carefully. Say for some particular reason I want to connect the output of this to a common drain amplifier. So when I say common drain amplifier, I am just connecting this point, the output of this common source amplifier, to the input of the common drain amplifier. This point is VDD, and this is common drain, right? So this is some DC voltage VB, and this is the output voltage. Now this is M1 and this is M2, right? So basically this is connected. I have connected this, and now if I look at the output, if I look at the output swing at this point, if I look at the output swing at this particular point, you can definitely say that yeah. So now this output DC level and this output DC level is having some difference. What is the difference? That difference is here, which is VGS. So let me give this number in continuous. This is M1, this is M1, this is M2, and this is M3. And this is M2, right? We have a difference of VGS here, and now for this transistor, we will have definitely have an overdrive, should have an overdrive voltage, which is VOV3, right? Now, when I look for the signal here, when I look for the signal swing here, this point, so this point can go to the top. You have to see the overdrive voltage of this, and the bottom you have to see the overdrive voltage of the M3 transistor. But referring back to the same input point, so I have connected this common drain amplifier at the output of a CS amplifier. Now after connecting this, if I look at the possibility of the voltage variation here, you can definitely say that your peak will remain same. So I will draw from here, this can go up to this point, But down, if you look at previously, your negative the negative peak cannot go up to 0. You have to have a overdrive voltage of M1. But now this negative peak, it is not only M1, you have a VGS voltage plus this VOV3. So I would say this is limited to this point. Why? Because now I should consider about the VGS voltage plus the overdrive voltage of the third transistor, right? Because at this specific point, at this point, when you have a voltage swing down to 0, that down to 0 should not cut off the transistors M2 and M3. And this happened when we had this cascading connection, or when we connected the output of a common source amplifier to common drain. Basically there is a hit, or there is a limitation in the output voltage, because the voltage headroom is limited here. Why? Because since we have the VGS voltage, this VGS voltage and this VOV3 voltage to be maintained for the saturation of those two devices, the DC level, or the signal swing at the output of the first stage cannot go below this voltage, or your signal cannot swing below this point. If this happens, then those two transistors may turn it off. Right. Yeah, Avinash, your question is, yes, there is definitely DC shift of VGS2, and that will happen for the signal which I am drawing at this point, right? If I draw the signal here, there is a VGS2 shift. So what I am drawing here is the same point. Both the signals which are seen in this pink and black, both are drawn at the same point. Which point? At the input of common drain. In the first case, when there is no cascade connection, that voltage can go as low as VOV. But when there is a cascade connection of common drain coming in, that node cannot go as low as VOV, because it has to maintain the saturation condition of the transistor M2 as well as M3. So it has to be one VGS extra than that VOV. That is what I have marked here as VGS plus VOV. Is that clear? All right. So yeah. So if you have questions, you can ask. So let me stop recording.